Yesterday we had discussed about correlations. So we discussed about Pearson correlation, Spearman's correlation, Kendall-Tau, biserial and point biserial. When we talk of these correlations, these are bivariate correlations. There is another type of correlation which is partial correlation. Apart from these bivariate correlations, what we discussed yesterday, this Kendall-Tau, the Spearman, Pearson, biserial, point biserial, all are bivariate correlations. There is another kind of correlation when you want to measure the relationship between two variables, but also there is a third variable that is affecting this relationship. And if this third variable is affecting this relationship, you want to have a control for that variable, or you want to make that variable constant. Let's say, for example, you have taken 1 liter of water and put it on a flame. If you put the flame to 100 degrees centigrade, the water will boil within 10 minutes. Let's say you have increased the flame temperature to 200 degrees centigrade. Now the time taken to boil the water is 7 minutes. So from this we can assume that there is a moderate negative correlation between temperature and the time taken for the water to boil. Let's say there is a 30% correlation. But will this correlation be always same in all the cases whenever we will boil water? Anybody?
No, sir.
No, sir.
It will vary.
What will cause it to vary?
The chillness of the water.
Yes.
Yes, its own the water at the room temperature, what it is actually.
Initial temperature of the water. So
Yes,
this
sir.
correlation won't be always there when the initial temperature of the water will vary. Let's say you have taken 1 liter of normal temperature, means water at room temperature, and 1 liter of ice cold water. In both the cases, if you increase the temperature to 200 degrees centigrade, it won't be case that both will take 7 minutes to boil. The degree will vary. Somebody from this session was mentioning, and also of course it has to be always 1 liter water. Let's say if it's 2 liter water, then again this correlation will vary. So actual relationship you won't be able to measure if there is a third variable present. Somebody in this session was mentioning that she is studying effect of ADSD. Is she present here?
Yes, sir. I am.
Okay. So let's say you want to study the effect of ADSD on the performance of the child, class performance. When children are suffering from ADSD, they are given special attention. Now, if this attention varies from the child to child, special attention given by the teacher. Let's say all ADSD students suffering from ADSD are there. They are having difficulty in performing in academics. You want to make a correlation that what is the effect of ADSD on the performance of the children in class. But if they are given different level of attention by their teachers, can you accurately measure the correlation?
No, sir.
No. So the level has to be the same. It has to be kept constant. So if this is the case, then we have to go for partial correlation. Are you getting my point?
Yes, sir.
Similarly, in the case of ice cold water, and when we want to test water, what is the effect of increase in the temperature on the boiling of water, then again the initial temperature of the water has to be controlled. When this is the situation, when you want to measure relationship between two variables, and there is also a third variable that is affecting this relationship, then the third variable needs to be controlled, and in that case we apply partial correlation. So let's say in our example that exam anxiety data, we know there is a relationship between exam anxiety as we have drawn those uh, scatter plots. There is a direct relationship between exam anxiety and performance. But this relationship is also affected by a third variable, that is time spent revising. If the student is revising more and more, then their anxiety will go down and their exam performance will increase. So, in the case of this third variable, time spent revising, we cannot accurately measure what is the effect, what is the relationship between exam anxiety and performance. So, in that case, we have to have a control for the time spent revising. So, I'll just share my screen and I want you to open that data set. Now, here we have seen yesterday that there is a relationship between exam anxiety and exam performance. Also, there is a relationship between time spent revising and exam performance, a negative correlation. Sorry, in revision time and exam, it was a positive correlation, whereas in exam performance and anxiety, there was a negative correlation. So, if we want to exactly measure, because this revision time is affecting the relationship between anxiety and performance, if we control this revision time, then what will happen? We can find more accurate relationship between anxiety and performance. So in this case, we are going to control the revision time. And the moment you control any variable while testing the association or relationship, it falls into the category of partial correlation. So in many of these studies, particularly the studies which are related to OBHR, where n number of factors affect behavior. Studies related to finance also, in stock performance, there will be n number of variables affecting the relationship which you want to keep constant. In the field of humanities, medical sciences, or in scientific studies where you want to have a cause and effect relationship, but that relationship is also affected by any third variable. So you want to have a control of that third variable or the external variable that is causing this relationship to be spurious. So to have a better clarity, it's always better that the third variable which is affecting this relationship should be controlled through partial correlation. So you can go to analyze to do it, go to correlate, and sorry, analyze, go to correlate, and from here rather than bivariate, select partial. Now select the variables. So we want to test exam anxiety, exam performance while controlling for time spent revising. Only this you have to do and click on OK. Now if you remember, I'll do another correlation, bivariate. And please remember, I am not removing this variable. Okay, when I am doing bivariate, you might be saying that, sir, if we want to have a relationship, why we are controlling time spent revising? Why not we test the exam performance and exam anxiety? We can do that, but only when this variable was not present. As of now, I am not discarding this variable. I am just controlling this variable, keeping it as a constant. So in general situation, let's see what is the relationship between exam performance and anxiety. If you see, there is a negative correlation and moderate, 44.1% between exam performance and exam anxiety. This might not be correct because there is a third variable also present. If I do a bivariate correlation with in presence of that also, let's say time spent revising also I have taken. So this will come to be 44.1%. Okay, there will be some positive correlation between performance and time spent revising, which is actually affecting this overall correlation. So this is correlation is not coming to be accurate because there is a third variable which I have controlled. The moment I have controlled this third variable, time spent revising, can you see any change in the correlation value?
Yes, sir. The
Now,
magnitude has decreased.
now there is a weak correlation. From moderate correlation, it is a weak negative correlation between the performance and anxiety when we control the time spent revising. Is this clear?
Yes, sir.
So when you have a situation like that, a relationship is affected by any third variable, then always, rather than going for bivariate correlation, please go for partial correlation, where you have a control over the third variable. Control means keeping that variable constant for all the observations. Okay. In that case, you will get better results. So now here we are getting 24.7%, which is a weak due to minus sign, weak negative correlation, but significant. If you see the p-value, it's less than 0.05. Just give me a second. So this was the case of partial correlation, where we are keeping one variable or the extraneous variable as constant. And this will is the basis also behind when we do regression. We all there also we keep something one variable as constant, and normally when we do mediated and moderated regression, then there is a need of keeping a control variable. But if you have to test the association where that association or the relationship is affected by any third variable, then of course, to have a better insights, go for the partial correlation. Any questions on this?
No, sir.
Okay. So now we are done with all kinds of correlations. Now let's move on to the regression. So can anyone tell me what is regression? Any idea what is regression?
Sir, good evening.
Good evening.
Sir, it's a statistical method wherein which we can estimate the value of unknown variable with the help of unknown variable, sir.
Yes, you have some known variables, and on the basis of that, you want to predict the unknown variable. What will be the value of that unknown variable? So basically, it is a predictive analytics technique which is used in almost all kind of studies. Most of the time, it is used in econometric models, in financial studies to predict. Also in marketing analytics, also it's used. It is used in HR, OB, almost in every field. And it's all about fitting the data points over a straight line. Okay. So when you fit this data, actually that straight line is nothing but the regression line. And the equation takes the shape of this y is equal to b0. Now remember my yesterday's example, every outcome is equal to model plus error. Outcome is the y which you want to predict. Model, in case of regression, correlation, it was only bx plus error. Now here, when we are putting this equation on a straight line, fitting this equation on a straight line, there will also be a third value that you will bring, that is the b0. Sometimes it is, in some books it is written a, somewhere it is written b0. It's the same. Basically, it is the intercept. And it is the point at which the regression line crosses the y-axis. If you fit the equation on a straight line, and since that y cannot be predicted to a level of 100%, something will go unpredicted, might be due to absence of some predictor variables or some error terms. So whatever goes unpredicted, we put it as error term. So let's say if my model is coming to be, the variance explained is coming to be 50%. So remaining 50% might not be explained due to error term, or the number of variables might not be sufficient, or there might be some other variable which may explain this. But given the variables which I am having, my model could be explained to the level of 50%, let's say. So the outcome of y that we are predicting can be predicted to a level of 50%. So let's understand this equation. So this is your model b0 plus bx. So y is outcome. So outcome is equal to this model plus error. In this b0, I have already told you it is the constant. It is also known as the intercept. Means it will tell you the value of, since it's a constant value, even if in any case the value of x is 0. Okay, x is your independent variable or predictor variable. B is its regression coefficient, as same as correlation coefficient we have seen. So if even the value of x is 0, then also you can predict the value of y with the help of this b0. Okay, so this b0 helps you to explain the value of y even when your x is, or your predictor variable is 0. So it is known as the intercept, it is known as the constant, and actually on a straight line it is the point where the regression line crosses the y-axis or meets the y-axis. B is the regression coefficient. So if you have only one variable, so it will be bx, means regression coefficient of the variable x. It is also known as the gradient or slope of the regression line. And as like correlation coefficient, here also it tells you the direction and strength of the relationship. So this is when you fit the line, this is the intercept and gradient. So intercept, I have already told you, the point where the line, this straight line crosses the y-axis. So you can see in this case intercept is the same, means at the same point these lines are crossing the y-axis, but gradients or the regression coefficient are different. They are moving in different directions. One is showing a positive relationship, another one is showing a negative relationship. Here you can see gradients are same, the B, okay, they all are showing going in positive direction, but they are crossing y-axis at different points, so intercepts are different. So hope you understand what is the intercept and what is the gradient. Intercept is the point where this straight line crosses the y-axis, whereas gradient tells you the direction or the strength of the relationship. Is this clear? Can I have a response?
Yes, sir.
Okay, fine. Now let's do our first simple linear regression. But there are few assumptions of linear regression which I'll tell you when we'll be doing multiple regressions. Because as of now, we don't have to bother much about the assumptions. Only one thing you need to know, that what is the error term, which I am mentioning many times. What is error term? Now, it is also known as residuals. So if you see this is the straight line. Data points are fitting on a straight line, but few data points are deviating from this straight line. Due to this deviation and due to these data points, 100% of the model cannot be explained. So what has gone unexplained is due to these error terms, residuals. This is also known as residuals. So those which lie above this straight line are positive residuals, and those which lie below this straight line are negative residuals. So always keep this in mind. So let's do one regression with one predictor only. That is simple linear regression. So let's open, I want you to open the data set album6.save. This one. Have you opened this?
Yes, sir. Opened.
Okay. Now we will take only only one predictor as of now to perform simple linear regression. This is the sales figure of the album. Let me tell you the scenario. What is the scenario? A music company owner, he wants to predict the number of albums sold in future. How many albums will be sold based on few parameters. He is having data of 200 albums. Okay. Based on this, he want to predict that in future how many albums will be sold. Now, how many albums will be sold in the future, that is unknown. That is what we want to predict, the why. What is known to us is the advertisement. This is advertising budget, how much has kept for advertisement, and each are in units of 1,000 pounds. So 10.26 means 10,260 pounds. Each are in units of 1,000 pounds. This is the sales of the album, number of albums sold. This is the airplay, means number of plays on radio. In a particular week, how many times a particular album has been played on a radio, and whether it is going to affect the sales. Can we predict the sales based on this? Also, there is another variable, which is attractiveness of the band, taken on an interval scale of 10 points. So the band which created that album, whether its attractiveness, based on that, can we predict how many albums will be sold? So we have three variables, predictor variables: advertising spends in thousands of pounds, number of plays on the radio, airplay in a particular week, and attractiveness or popularity of the band on a 10-point scale, which made that particular album. And this first observation is for first album, second is for second album. Each observation is independent of each other. So like this, he has taken 200 data of 200 albums, and now he wants to know that based on these, how many albums could be sold in future. So first, let's say we are interested in knowing how can we predict the sales based on advertising only. This is the case of simple linear regression, where you are trying to predict the sales based on only one variable or one predictor variable, that is the advertising spent in thousands of pounds. Fine. So go to analyze, regression, and linear. Now, why I'm saying it's linear? Because the basic requirement of a linear regression is that there should be a linear association between the variables, and linear association can be tested through scatter plots. Already I have told you. So first, let's see that the assumption of linearity is followed between this predictor variable and the y or not outcome variable. So on y-axis, I will take album sales. On x-axis, this advertising budget. Fit linear total. So if you see here, we can first thing, the relationship, direction of the relationship is there, that as advertising budget increases, sales also increases. And this relationship can be explained to the level of 33.5% only. See the R square linear. So as of now, we are not estimating that how much variance will be explained. As of now, we are only trying to know that whether there is a linear relationship between the variables or not. The first main assumption that you want to have, because it's a linear regression. So there should be a linear association. Now go to analyze, regression, linear. and take the independent, take the album sales, in independent, take the advertising budget. Now, second thing is which method we have to enter. This normally people avoid, but it has a very influential role in making your regression model. As of now, since I am having only one predictor variable, so I need not to worry about this method. The moment I will be having many predictor variables, I need to choose. So as of now, by default, let's leave it as enter method only. Here you can have, we need not R square changed, no multicollinearity diagnostics because only one variable is there. So we'll leave it as it is. Plots, as of now, we won't be having, no need of that. Simply just run it. So this one, first table will tell you how many variables were entered or removed. So as of now, we had only one variable and it was entered into regression. Now, what is meant by this variable enter or remove? When we'll be doing multiple regression, I'll explain you because this has the relevance there only. Now coming to the second table. Second table tells you about the correlation, the R, 57.8% positive correlation. And how much variance can be explained? R square, 33.5%. Isn't it?
Yes, sir.
Yes, sir.
So we can explain or we can predict Y based on X to the level of 33.5%. Now here there is a adjusted R square also. Which one should we report? R square or adjusted R square?
So R square.
So what is the role of adjusted R square? If it is giving you this, there is some role of adjusted R square. See, this adjusted R square is used for cross validation of the model. If there is no much difference between R square and adjusted R square, then what you can say that your model stands valid, this predictive model stands valid throughout the population because we have taken a sample of 200 observations. Based on that, we are building a regression, a predictive model, and we also want to generalize that model to the entire population. That in event of all albums, this model will be explained to the level of 33.5% and it will be a valid model. Let's say if you randomly draw another 200 samples from the population, the level of predictive model that you will get and the level of variance explained will be the same. So if there is no much difference between R square and adjusted R square, then you can say that our model stands valid. We can extend this model from the sample to the population. If there is a difference, much difference between R square and adjusted R square, then you can put it as a limitation that this predictive model does not hold true in the entire population. It is only limited to my sample only. However, then you have to look at your data because whenever you are doing a predictive model, you are doing not for this sample, we are doing for the entire population. Are you getting my point?
Yes, sir.
Okay. Now, what is the significance of ANOVA table in regression? When I was telling about ANOVA, I have mentioned this thing that when you will be doing regression, ANOVA table will be made. What does ANOVA table tells you? Any idea? ANOVA table tells you about the fitness of the model. So how we will assess the fitness of the model? We will assess the fitness of the model by seeing the F value and the significance. So for the, see, this one is not telling you the fitness of the model. It is telling you the validation or generalization of the model. And this one is telling you about the fitness of the model, whether your model is a good fit or not. So for a model to be a regression model or predictive model to be a good fit, this F value should be greater than 1 and should be significant. So here you can see that the F value is far more than 1, 99.587, and significant also. So this model is a good fit. Now coming to this table. So I already told you that the model is, the statistical model is Y, which is here album sales, is equal to B0 plus Bx, because we have only one variable. So if you see this table, can anybody tell me what is the value of B0?
Sir, 134.140.
Is equal to 134.140
.140. 0.
plus, what is the value of B?
So it is 0.096.
0.096 into, what is the value of X? No value, but because value of X you have to take, so into advertising budget. This is your predictive model. Now this model, if you put, let's say, advertising budget, let's say if it is 10, if you are putting, so how many albums will be sold? You can simply calculate it. So 10 means, okay, what does it tells you? That 1 unit of increase in advertising budget will increase the album sales by 0.096 units, where album is sales is into where advertising budget is into thousands of pounds. So you can say that if I put it as $1,000, sorry, 1,000 pounds, what will be the value? How many albums will be sold? If I put the advertising budget, if I spend 1,000 pounds on advertisement. So let's see this formula. So it will be 0.096 into 1,000 plus 134.14. Sorry, some error in calculation. Let me check. 0.096 into 1,000 is, okay, 96. It will be plus 134.14. So total of 230 albums will be sold if I spend 1,000 pounds on advertising budget. Similarly, you keep on changing this value and you can predict how many albums will be sold. Is this clear? This is predicting the album sales based on only one variable, one predictor variable, that is advertising budget. Is this situation clear?
Okay, sir.
So this is our predictive model which we have made, a regression model. This regression model is fit also, good fit due to f greater than 1 and significant. And whatever we are predicting here, 230 albums sold, this prediction model stands true only to the level of 33.5%. This might be due to because we have not included other variables, due to error terms also. But to the level of 33.5%, the accuracy of the model is there. And second thing, this model can be that we have made here can be generalized to the entire population because it is cross validated. There is no much difference between R square and adjusted R square. So these three tables are telling you three different things about your model. Now, if you see your data, so we have taken only one. Now, what if you take more than one? Then if you are taking more than one predictor variable, we have three predictor variables, x1, x2, and x3. So few things needs to be taken care of. First one is linearity. Already I told you through scatter plots, you will check the linearity of each variable with the outcome variable, that is sales. Then only you can perform linear, because this multiple regression is also a linear regression only, extension of simple linear regression where you are putting more than one predictor variable. That's it. Now, before I move on to assumption, one thing I would like to tell you very clearly, that when you choose your predictor variables, choose it very cautiously, because SPSS is just a software. If you'll give them some numbers, it will give you some numbers in return. That's it. Whether a predictor model is whether a predictor variable that you are taking is a good predictor or not, that is very important, and that should be taken from literature review. From the literatures, what are the variables that strongly predict your outcome variable? Only you should keep. There could be 100 factors that could predict an outcome, but whether all those 100 are important, you have to see to that and choose only those variables which makes sense. Don't add noise to your model. Like, let's say in our case, we all know that advertising has direct effect on sales. So we have taken advertising. Number of times it will be played on the radio. Of course, people will come to know about it, that album. Like in our case, now we don't listen to the radios, but number of YouTube watches we see, there are likely chances that we are going to purchase that album. Though on YouTube it's available for free, let's say it's only on YouTube, or let's say it's advertised on TV or played on FM radio, then there are higher chances because we are listening to it again and again. So this could be one predictor. Popularity of the band that created a music album, that could also predict the sales. A good band will predict, means if there is a good band whose popularity is high, chances of the sale of the album created by them is also high. But let's say we also want to take, so these three variables we are taking, that seems logical. But is it also sensible if we want to take that what was the cost involved in making the album? Can the cost
But
involved in,
if the literatures supports this variable, like the cost of the song or the
Hmm.
sales price affect like the amount that we have to spend. If a one cd is of 5,000 rupees, I may not purchase that. I would just prefer to view that the song on YouTube. So it
Hmm.
might affect if the literature supports that.
Fine. So if literature supports that, then you take. Otherwise, if we take this particular scenario, so I'm not talking about the price. I'm only talking about the cost involved in production. Price is altogether. Let's say he is keeping his uh, profit margin very less, then price could be affordable. So price could be a significant predictor, but cost involved in production. When we go for purchasing any album, do we really are we really interested in knowing what was the cost to the producer for making this album?
No, not particularly.
Not particularly. So if we are taking that also in account, don't you feel that all that was what that is one of the variable for the album producer, okay, the album company manufacturer. But for a salesperson or from the sales point of view, does that really matters to the consumers?
No.
No. So if you are taking that variable, you are what you are doing? You are simply adding noise to your data, isn't it?
Yes, sir.
So choose your variables. Two things you have to keep in mind when you are doing multiple regression. Choosing the variables very cautiously and selecting on which of the method of regression you have to choose. Whether it has to be enter method, whether it has to be hierarchical method, whether it has to be stepwise, force entry, whatever, which we avoid. So we have 10 variables, we put all 10 variables in the model. Please don't do that. Select only those variables which are indicated by literature. Like most of the literature will indicate that workplace, this what you can say, workplace culture, monetary benefits, uh, work-life balance, working hours, all this could predict the productivity of an employee. So you can keep. But can you also include the quality of furniture kept in the office to understand the productivity of the employee?
It may have a very minimal effect
Very
on
minimal
the.
effect. That is not a very strong predictor, isn't it?
Yes, sir.
So it's better to avoid that variable, right? So you have to choose the variable very cautiously. First, it should be logical. Second, it should be supported by literature. This is the first step in making a good regression model because ultimately you are predicting something. Second thing is that you should choose the method of regression very cautiously, which you want to choose. So if we can we have 5 minutes break and then we will resume the session. So that
Yes, sir.
yeah.
Yes, sir.
Okay. So let's resume the session. Are you there?
Yes,
Yes.
sir.
So after
Yes, sir.
choosing on your variables cautiously, and I'll come to the method later. First thing you have to check for few assumptions. Assumptions of multiple regression. So first one is the linearity among variables. Each independent variable should be linearly associated, have linear association with the dependent variable. I'm writing here tested through scatter plots. Second assumption is independent errors. This simply means that residual errors should be uncorrelated with each other. Each residual error should be independent. This one residual error should not affect the another residual error. Right? This is also known as the case of no autocorrelation. Right? Tested by Durbin-Watson test. Test ideally ideally the value and range between 0 to 4. That is thumb rule. If there is independent residual errors, because when we talk of regression, we focus more on the residual errors. So there should be no autocorrelation, means one residual error should not be correlated with another residual error. Or this is also known as the case of independence of residual errors tested through Durbin-Watson. There should be homoscedasticity. Dasticity. Its homogeneity of variances should be there. Variances. This you can check through Levin's test of homogeneity of variance or Bartlett's test also. Any of the method you can choose. Fourth one is, see here we do not check the normality of data or variables. We check the normality of residual errors. So the residual errors should be normally distributed, because there is nothing called non-parametric regression. Okay. So in every case, if we have the data which is not normally distributed, then we can go for its non-parametric equivalent. Regression, if your data is not normally distributed, don't care about it. Simply you can run regression, but you have to check whether errors are normally distributed or not. Errors. This can be checked by normal QQ, normal EP plots, probability plots in SPSS, normal QQ plots, in R and Python, or there is a multivariate normality test known as Anderson-Darling test, which is not available in SPSS. You can do in R or Python. This is the numerical method. This is the test for multivariate normality, Anderson-Darling test in R or Python. See, it's a linear association, so linearity has to be there. Residuals should be normally should have no autocorrelation. There should be homogeneity of variance or homoscedasticity. Residuals should be normally distributed, and one very important point: no multicollinearity. This simply states that the independent or the predictor variable should not be highly correlated with each other. And this you can assess at the very primary level when you are calculating Cronbach alpha for your questionnaire. If already I have told you Cronbach alpha is more than 0.9, it is something 0.97, 0.95, then this shows there is a multicollinearity, and when you will be doing regression, you can check that multicollinearity. Why it is important? Let's say in our case we had three independent or three predictor variables, x1, x2, x3. Let's say x2 is not able to predict y, but since it is highly correlated to x3, so it is borrowing its property from x3, and in the model it is showing that it is affecting y. It can predict y due to the borrowed characteristic from the variable x3. Actually, it is not the predictor, but it is borrowing the its properties from x3, and that why it is borrowing, it is because it is highly correlated. So, will my model, predictive model, will be correct?
No,
If there,
sir.
No.
No,
so that,
sir.
so this is one of the important things which has to be taken care of. Multicollinearity should not be there, and this is the basis why we should do. This is tested through EV tolerance value and the main test is VIF, variance inflation. So for no multicollinearity, EV should be greater than 0.2 and VIF should be less than 10. However, if VIF is ranging from 1 to 3, shows no problem of multicollinearity. So the perfect case. Perfect case. If it ranges from 3 to 5, it's okay. If it ranges between 5 to 9, some problem of multicollinearity. still can be adjusted by looking at the data, correcting the data. However, if it is greater than 10 or greater than 10, serious problem of multiple effect. Always keep this range in mind. Then choosing the method. If you see in SPSS, now we'll be putting these three variables, and then I will explain you about the different methods. So let's go to analyze a regression, linear. So album sales will be there. What I will add here? Two more variables. So advertising budget, number of plays, attractiveness. Now coming to the method. Here we have enter method, stepwise method, remove, backward, forward. What does enter method does? Enter method, when you are not aware, when you are not sure that which of these variable would be a strong predictor of the dependent variable, then you can choose enter method. Means all variables, your dependent variables will be regressed upon your independent variables simultaneously, all at once. But this method should only be adopted. Most of the people adopt by default this method because by default it's enter method. But in my view and what I have studied till now and what my experience says, this enter method should always be used when you are very sure, when you are not sure that in which order the variance is explained or which one is the strong predictor. When you know that which one is the best predictor, then put them this stepwise method. So this enter method is known as forced entry. You are forcing all your three variables at once, and let SPSS do simultaneous regression. But if you are sure from the literatures you come to know that, let's say, advertising budget is the strongest predictor of sales, so you keep it this method, you select stepwise. This is also not stepwise, yeah. And you can, but when you are choosing this stepwise, where is the problem? Suppose, when you are sure that this is the advertising budget is the strongest predictor, leave the method, select first in the first step this one, and if you are also sure that number of plays, then you can put it in the second step, then you can put in the third step. However, let's say in our case we are sure that advertising effect do have a is a strong predictor of album sales, but we are not sure about these two. So in the next step we can include these two at once. Okay. However, if you are sure about each and every step, then you can go for next. Means you are making an additive model. First you are regressing with the strongest predictor, then weaker than that, then weaker than that. So since we are based on your literature review and based on your logic, and this you are choosing on your own. This is known as block-wise entry or hierarchical regression. Now, when you are choosing all these at once, because you are not sure which of them will explain better this album sales. You don't have sufficient literature to understand that. Then either forced entry method you can use, or you can use stepwise. Now, what is the difference between the blockwise entry that we had done and the stepwise? In blockwise entry, we choose the variables in the order that which one will be first regressed, which one will be regressed in the second step by our own logic and by our supported by our literature. But when you choose stepwise, the same hierarchical regression is performed, but this time not by you, by SPSS. And how it chooses that which variable will come first? By on the basis of mathematical calculation, it will check that which of the variable is explaining the album sales to the maximum through mathematical calculations. It will keep it at the first. Then the remaining it will check for, let's say, advertising budget has explained to the level of 60% variance. Let's say it has checked. So, and it will keep it in that order. Then it will search for the remaining 40%. Let's say the remaining 40% is also explained by number of plays on the radio. 100% achieved. What will happen? It will drop the attractiveness of the band. Though it was an important variable to you, but it has removed it because 100% achieved. Or based on the data, logically it should be that advertising budget should be regressed first, but based on the data, based on the mathematical calculation, it is finding that attractiveness, because what data you have collected, based on that it is saying that attractiveness of the band is a strong predictor. So first it will regress that. Then it will check for the remaining one, and if it is finding that a number of plays on the radio is the second highest predictor, maximum variance is explained by number of plays on the radio, it will put it in the second step, and advertising budget it will put in the third step. Though it is taking all your variables into account, but the order is not proper because you are letting a software to do. That is the serious problem with stepwise. Let me explain it in a different manner. Let's say there is a cold weather outside. To protect you from cold, you have jackets, you have socks, you have shoes, you have trousers, you have shirt. Now, if you ask SPSS that what should I wear and in which order so that I could be saved from cold, so what it will suggest you? Maximum protection you will get from what? Jacket, isn't it?
Yes, sir.
So it will tell you that first you wear the jacket. Then over the jacket, because that maximum variance is explained by jacket. It is building a predictive model that if you wear the jacket first, you will be saved from cold. Then it will ask you to wear your shirt and trousers. Then it will ask you to wear your socks and undergarments over that, because that is the least explaining and least saving you from the cold. So it is taking all variables into account, but based in the order which it seems fit based on the mathematical calculation that whether which one will explain the variance better. And in that case, few of the variables might be removed, which is of importance to you. So please try to avoid stepwise regression. Don't let SPSS determine which variable will be regressed first. Either you can choose, if you are sure, please choose this hierarchical regression, blockwise entry, which is always preferred the best, or choose or take all at once and choose the enter method. The problem with this stepwise method is this only. So try to avoid it. Remove backward forward methods are as same as the additive methods. Okay, as same as this stepwise method. Only in forward and backward method, what happens that each time a predictor is added to the equation, a removal test is done based on the least useful predictor. So it will remove, it will do backward, forward, all these things it will do. So main methods are three: hierarchical, that is blockwise; enter method, force entry; and stepwise. So the most preferred is the blockwise entry. If you are sure about your variables, if you are unsure about your variables, enter method, all regress simultaneously. When you will be using stepwise, there are chances that based on the nature of the data, your variables might, few of them might be removed or put in a wrong order. There might be chances. I'm not saying that uh, it is not the correct method, but there are the chances. Given that my example of cold and how you can be protected from cold, right? So please take this in account. So here we know that advertising budget, almost all of the literature tells us that advertising budget is the strong predictor of sales. More you spend on advertising, sales increases. So at the first step, I will take this. If I'm sure of that after that this should come and after that this should come, or after that this should come and this should come, in which order, then I can go for it. If I'm not sure, then in the next method I can put all these two together. So what will happen at the first stage? Only album sales will be regressed with advertising budget, and in the second step this will be regressed with these remaining two simultaneously. Are you getting my point?
Yes, sir.
Yes, sir.
Okay. Now, after putting this, select statistics. Here, estimates confidence interval, we are keeping it at 95%. If you want to change it, you can, but for social science humanities research, we keep it. R square changed also we want, because we are doing regression in two steps. First with one variable, and in the second step, two more variables. So we will see that whether R square is changing or not, in which case the model is a good fit. Descriptives, part and partial correlation, if you want to check, you can keep, and collinearity diagnostic. This is multi-collinearity, to check multi-collinearity. Then auto-correlation of residuals, Darwin Watson, I have told you. Continue. Then plots, to check the normality of residuals. There are many plots. So there are many variables. This is dependent, is the dependent variable. This PRED is the standardized predicted value. This is the standardized residual value. This is deleted residuals value. This is adjusted predicted value. This is again standardized residual value. This is standardized residual value. All these are there. But when we have to do normality test of errors, we take into account this Z residual, that is the standardized residual on y-axis, and standardized value of predicted values. Okay, ZPRED, that is the standardized predicted value at x-axis. And you can select histogram and normal probability plots here. Or only if you select normal probability plots, it will produce normal PP plots, which is sufficient for you. Continue. Now, if you want to save them, save the outcome as or your predicted values, then you can select these as unstandardized, standardized, adjusted. Okay. As of now in regression, we are not checking about the distance. Otherwise, you can take Mahalanobis or Cook's or leverage values. So only we are saving this instant predicted values, means out of the regression equation, what will be the value of album sales, that also will be saved. Continue. Style, nothing is required. We are not bootstrapping the model. Bootstrapping is altogether a different thing. Click on OK. Now see, this descriptive statistics, okay, mean, standard deviation, all it is giving you how many variables were there. This correlation table. Now here if you see variables removed and entered. So none of the variables were removed. At the first step, we added advertising budget. At the second step, we added simultaneously attractiveness of the band and number of plays on radio. And we have two R squares, right? In the first case, what we had 33.5% R square. Can you see this?
Yes, sir.
Yes, sir.
Now, this is the same result that we got when we had done simple linear regression using only advertising budget. So when only advertising budget is used, taken as a predictor, the model can be explained to the level of 33.5%. But in presence of the other two, our model have improved or not?
Yes, sir.
So now, if we take all these three variables, the model could be explained to the level of 66.5%. So our model has improved, and hierarchical regression tells you about at every step, if you are adding by a variable, how much your model is improved. So we can see that at the second step, when along with advertising budget, we also added attractiveness and number of plays on the radio, model has improved. And in both the cases, you can see there is no much difference between adjusted R square and R square. So you can say that the model could be generalized to the population. F value, you can see it is more than 1 and significant. So the model is a good fit. Now coming, and even ANOVA is also telling you the same, right? In both the cases. Okay. This is the F change statistics. We basically have to see this F statistic more than 1. And the moment we added the other two variables, we got higher greater values of F. So our model is significant. Our model is a good fit. Now, before coming to the model, let's see the assumptions. Durbin-Watson should range from 0 to 4. Here what we are getting? 1.9, right? So there is no autocorrelation. There is no autocorrelation. First assumption met. Linearity we had already checked. Now coming to the tolerance value and the VIF value. Tolerance value should be greater than 0.2 and VIF should be less than 10, and if it is ranging from 1 to 3, then it is very much desirable. So you see, in all cases our tolerance value was more than 0.2. Our VIF value was close to 1 only. So there is no problem of multicollinearity also. Is this clear?
Yes, sir.
So linearity we have tested, no autocorrelation, Durbin-Watson. Homogeneity of variance you can test through Levin's test or Bartlett test. Bartlett test actually not available here. In R and Python you can do. Multicollinearity problem solved, no multicollinearity. Okay. And now let's see the normality of residual errors in the PP plots. Now this is the normal PP plot. If these data points are very close to the straight line and in symmetry, then there is normality of PP plots or normality of residual errors. If they are scattered, then normality of residuals is not there. So in our case, you can see all are very close to the data points. All data points are very close to this diagonal line and are in symmetry. So normality of residual errors is also there. Means all assumptions are met. Now let's see at our model. So this tells you about the beta value. So which one we will take? First one or second one? The
So the
constant.
second one.
Because at the second step we added two more variables, right? So this value you will take. So now our model will be y is equal to, where y is equal to album sales is equal to minus 26.613 plus 0.085 into advertising budget. Simply means 1 unit increase in advertising budget, or 1 unit of advertising budget, where 1 unit is equal to £1,000, will increase or will have 85 albums sold, right? Plus 3.367 into number of plays. If we increase the number of plays by 1 unit, 3,367 album will be sold. Plus 11.086 into bigness of band or popularity of band. If the attractiveness of the band is increased to 1 point, let's say it was 7, now it is increased to 8, then 11,086 albums will be sold. Right? Now, can you tell me which one is the best method here? On which, out of these, which one should the album company focus upon? Can you tell me?
So the attractiveness of band.
Okay, that is the best method. But should the album company go for it? Should the album company go for it? Suggest.
No, sir.
Why? This is one of the best method.
Because when we assess the advertising budget alone, it was having an impact of 33%.
No, it's not about percentage. See,
Okay.
if you are spending 1,000 pounds on advertising, only 85 albums are sold, right?
Yes, sir.
So this is of course not a
Hmm.
suggested method. Means total album sales you will get through this formula by putting all. But which one should be focused upon if you have to suggest? So advertising budget is of course not a feasible solution. It is not a
Hmm.
strong predictor.
Yes, sir.
Attractiveness of band is the strongest predictor. Means if you increase the attractiveness of the band by 1 unit, 11,086 albums will be sold.
Yeah.
But now here the problem is increasing or having impact on the attractiveness of the band. Is it in the hand of music album company?
No.
And second thing, more and more popular the band will be, more and more money it will charge from the album company,
Yes. Yes.
isn't it?
Yes, sir.
Or sometimes album company has to sponsor events of the band so as to make it popular. That will again have a cost,
Yes, sir.
right?
Yes, sir.
Now, if you see number of plays on the radio, okay,
Yes, sir.
if one more time the album is played on the radio, it is yielding a output of
3,000.
3,367 albums
67.
sold. So the best method is attractiveness of the band, but the optimal solution, always we try to find out the optimal solution, and the optimal solution
Increase in the number of plays at the
is
radio.
because that actually won't cost much and the
Yeah.
yield will be high.
Yes.
Okay,
Yes, sir.
now this is one regression model that you have made. Now second thing, what is the what is this standardized these are unstandardized beta coefficients. What does this standardized beta coefficient tells you? This indicates about the standard deviation. Okay, this simply tells you about standard deviation. So if advertising budget increases by 1 standard deviation, album sales increases by 0.511. If you want to report, you can report this also. Okay. And what is 1 standard deviation? This one. 485.65521 multiplied by 1000 because it is in thousand of pounds. So 485.65. Okay.
Okay, sir.
This is one standard deviation. If so, this is 1 standard deviation. So standardized one first. Let me write 1 standard deviation is equal to 485.655 pounds. So this standardized beta value will tell you that if album sales increases by 1 standard deviation, means if it is 485, it is 4,85,655 pounds, then album sales will increase by 0.511 standard deviation. Now 1 standard deviation for album sales is how much? Eighty thousand
80.699.
in thousands, na? So
Yes, sir.
80,699.
Yes, sir.
So 1 standard deviation will lead to 0.511 standard album sales. So how many albums should be sold if there is a change of one standard deviation, which is 655 pounds? It will yield 0.511 into 30,699 albums, which will be equal to
So 41,237. No. 41.237189.
almost 41.24, right?
Yes, sir.
41,240 albums.
Yes, sir.
So if you are spending this much pounds, okay, 485,655 pounds, then album sold will be 41,240. We are actually just cross-checking our model with this. Similarly, in case of airplay, it is 0.512, if you see.
Yes, sir. It was 0.1512.
0.512. So for each airplay, each time airplay is increased, how many albums should be sold? This tells you about standard deviation. 0.512 into 30,699.
So it is for 41.32.
41,320 albums should be sold.
Yes, sir.
And if we go for attractiveness, if attractiveness is increased by 1 units, then how many albums will be sold? 0.192 into 30,000, 3699. How many albums are sold?
So it is 15.5.
15.5.
Yes, sir.
Now, if you cross check with this standard deviation, standardized value, now which one is the better solution?
So airplay.
Airplay is always the better solution, because here for getting 41,240 albums sold, you have to spend 485,655 pounds, isn't it?
Yes,
This much pound you have to spend to get this much sales. But here only increasing airplay by 1 unit, 1 standard deviation, you can get a yield of 41,320 albums sold, which is highest. And here, even if you are increasing the attractiveness of band, which will incur again cost to the album company, only 15,500 are sold. So first thing is that you make this predictive model, see which one is the optimal solution, and then you cross check with the standardized coefficients also, because these will tell you about standard deviations. So through standard deviation also, airplay is coming to be the better solution as compared to others. So overall album sold you will get by this formula. But which one is the best solution, you will find through this standard deviation or standardized beta coefficients, which you can calculate by taking this standard deviation. Since it is in 1000, so it will be multiplied by 1000. If it is in 1 unit, then it will be 80.699. Then you take into account the standardized coefficients and what is the value of 1 standard deviation of album sales. That again you will get from here only. Okay, and you can calculate on this basis which one is the best solution. Is this clear?
Yes, sir.
Yes, sir.
I believe whenever anybody has taught you regression, they have not touched upon this point, standard deviations.
Yes, sir.
So this is something which you need to, because see, regression model you have made, you can predict total album sales. But you have to also tell the company, or whenever you are doing regression model, that out of this, which one should be the best method to go for. This one you can calculate through standardized beta values and standard deviations, right? All assumptions fulfilled, we have checked, and we found that airplay is the best solution. And theoretically also, if you see from this model, then also you can see that attractiveness of band, though it is a strong predictor, but it will increase high cost. Okay. Whereas this is the optimal solution. Here also through standard deviation, it is coming to be the best solution. At the end of the day, you have to suggest a solution, right? All assumptions have been fulfilled. So by regression, we solve this problem. Is this clear?
Yes, sir.
If you have any confusion, you can just ask me right now, or we can discuss later on also.
Sir, I have some questions.
Yes, please.
So my first question is, if I am checking the multicollinearity of the IVs, independent variables,
Hmm.
and what will be the minimum value of the correlation where I will say that it is not highly correlated? I can take that in my regression analysis.
So you want to test this multicollinearity through correlation?
Yes.
It should be less than 25%. Weak correlation.
Okay. And is it
See,
necessary that?
still till 50% we are okay with this, but it should not be beyond 50%.
Okay, okay. So for the regression analysis, do I need to firstly do the correlation, then decide the particular variables and then put them in the regression analysis?
You can do like this also, or you can, while doing regression analysis, you can first check for this VIF values also. Anyways, you can do it.
Okay. If I have two scales which have multiple subdomains, and there is no particular sub complete total, like I am using one resilience scale which
Hmm.
has components of community
Hmm.
based resilience, and then the personal resilience, school based factors, and then home based factors. So there are various subdomains in that resilience tool.
Some questions, right?
Subdomains, and I am
Sub,
getting various, like total
some,
number of.
some, some background voice is coming. Yes, please continue.
Yeah, yeah. So in my resilience questionnaire, I am getting one score for home based factors, one scale, one for community based,
Hmm.
one for school based, and one for personal. So I have four subdomains, score
Hmm.
on four subdomains, and no particular total resilience of the child.
So
So
you submit all these scores, you will get the total resilience.
in that they have in their literature they have said that the personal resilience and the factors, social factors, the home and the school and the community are
Hmm.
two different domains, but they somewhere affect the resilience of the child. So
Hmm.
I cannot club all them together
No,
to get one
I'm not talking of all together. Only those things which are related to resilience.
social factors. All the social factors I can club them, and the personal I can club them, so then I will get.
Separately, yeah.
Okay,
Not
okay.
clubbing every separately you should club. However, if you want to do regression on subdomains, then you can keep their original scores, right? And test them for multicollinearity.
Okay, so I can take all of them and then do the multiple check and then to take them whatever is fitting that in that.
See. When you are having two domains, which subdomains, of course you will go for one thing, that is the what to be said, validity.
Okay, validity of the tool.
Validity of the tool, of course you will go for.
Yeah.
And when you will go for the validity says that there should be discriminant validity and convergent validity. So of course all those domains measuring the resilience will be personal resilience, right?
Yes, sir.
Should be highly correlated with each other.
Yes, sir. They are highly correlated.
They will be. So this is not, you are regressing these two variables separately. Now, one is resilience, another one is.
Social support.
So there should not be high correlation between subdomains of social support and subdomains of resilience.
Okay, I got it.
Means you will be getting discriminant validity. Okay, and convergent, of course, you have to get, because all those subdomains should point towards resilience only. They should not point towards any other factor.
Okay, sir.
Are you getting my point?
Yes, sir, completely.
So if they are, see, subdomains of resilience are having this correlation among themselves, good correlation, then that's a good thing. They should, when you will do regression, then you will check this multicollinearity between the overall resilience and these things, the points leading to the this personal or whatever social factors, right?
Yes, sir.
I hope you got your answer.
Yes, I got my answer. Thank you.
So if you don't have other questions, then we may wind it off.
Sir, one question.
Yeah.
From
Yeah.
sir, regarding the predictability of a model, this multiple regression model, for maybe for the cases of studying religious sentiments and all, wherein people don't easily give answers so easily. So what should be the predictability range, means develop R and all? How to how do you have any specific criteria that up to this level it is a good predictor model, and beyond this it's not a good predictor model, something like that, sir?
Sir, normally a predictor model should at least 50% at least.
Yeah, but below
The
50%.
voice is echo. I did not get that. Jagat sir, if you can mute yourself. Sorry.
See, predictivity of a model, actually, it also depends on what kind of study you are doing. Like you are trying to study religious sentiments, of course, the predictivity of the model will not be high. So even 40%, 30% would be acceptable. But if you ask me that what should be the accuracy or what could be the predictivity of the model, at least I would prefer 50%.
So actually, I had undergone one study. I had taken up on study long back, maybe 7-8 years back. So while collecting the data, the people were very reluctant in giving some answers, maybe their income, and then what's called the marital, the use of what is called contraception and all. So which were very essential information for developing the model.
See.
Yeah.
Getting questionnaire filled is an art.
Yeah.
So let's say
in
you
that
didn't
case,
got
the predictability was maybe around 30% or 35%. So just wanted to know, and I had gone through some literature. Then I just am unable to recollect the name of the econometrician. He had suggested that in some cases, like wherein the vulnerable questions are being used, or are like religious sentiments, so the predictability may be very low, even around 25 to 30%. I read somewhere.
That's what I'm saying. It all depends upon the nature of the study you are doing.
Okay.
So the kind of study that you are doing, even 30% is okay, provided, because the remaining things will be due to the error term. You didn't got proper response, data
Yes.
so this will come into your limitation part. Okay.
Yes.
You simply report that only 30% was achieved due to these factors. People were elected.
Yes.
However, whenever you are going for survey, it's an art. But if you are not getting, fine, you report this. But you see, there should not be much difference between your R square and adjusted R square.
Okay.
So that you can generalize, because ultimately you are taking this study to generalize it on a population. So your 30% predictability is okay, provided it is generalizable, and it all depends on the nature of the study also.
Okay.
That's fine.
Thank you, sir.
Yeah. Anything else?